Okay, this is the 19th video on our linear algebra series. Last time we have lecture 18, singular value decomposition, and mm, and the other one is polar decomposition. Today we will begin our new chapter, the operator on complex vector spaces. We will start with some convention. Recall here F is just complex numbers or the real numbers, but because this chapter is on complex vector spaces, we will deal mostly with complex. V is a vector space over our F. And the additional assumption here is we will avoid trivialities. So we will consider V to be not equal to the trivial vector space. We will start with the first topic for this chapter, the generalized eigenvectors and nilpotent operators. So this is 8.8a. So generalized eigenvectors and nilpotent operators. But we will just have a little time for nilpotent operators. We will spend much of the time on developing the concepts necessary for and then discussing eigenvectors, the generalized eigenvectors. So we will begin with a proposition. From now on, instead of theorem, I will just refer to my theorem before as proposition. So we will study null space of powers of operators. And then let's begin with a statement. This is proposition 8.2. If we have a linear operator T, then you have this sequence of increasing null spaces. Then the null space, which is just the null space of T raised to 0, is contained in the null space of T raised to 1, and then it's contained in the null space of T raised to K, and this is contained in the null space of T raised to K plus 1, and so on. So for the proof, it's just it's easy. So let K be a positive integer, and V be in the null space of T raised to K. If B is in the null space of T raised to K, then your T raised to K of V is just 0. This implies that T of T of T raised to K plus 1 is just T raised of V, T raised to K plus 1 of V, which is equal to T raised to T of T raised to K of V. This is just equal to T of 0, and we know that T of 0 is 0. Thus, this one this V is also the null space of T raised to K plus 1. The second proposition is the following. If we have two consecutive terms in the sequence are equal, then all the later terms are equal. So what this says is that there is a non-negative integer such that your null of the power of t to that integer is already equal to the next, the null space of the power plus 1 of that integer. So let me state that proposition as a proposition. T here is again operator, m be a positive integer, non-negative integer, such that your null of t to the m is equal to the null of t to the m plus 1. Then your null of t to the m is equal to the null of t to the m plus 1. And this is also equal to the null of t to the m plus 2, and so on. That is, this sequence stops. Okay. Shall I prove this? Okay, let me quickly prove this one. So we have already shown that the null of t raised to m plus k is inside the null space of k, m plus k plus 1. This is previous, the previous proposition. And then we want to show now that the null space of d m plus k is inside the null space of e raised to m plus k plus 1. This is what we want to show. So let b be in the null space of t raised to m plus k plus 1. Okay? This means that t of m plus k plus 1 of v is equal to t of m plus 1 times t k of v. And then this is equal to 0 by here. What this means is tk is of v is in the null space of this t raised to m plus 1. And then we know that this is just equal to the null of t raised to m. Thus, t m plus k of v is equal to t m tk of v is equal to 0, which implies that v here is in the null space of t m plus k as desired. So we have shown this inclusion and we have shown this inclusion. This one and this one. This means that we have the required result. Okay. In fact, this proposition raises the question whether there exists a non-negative integer such that this sequence of null spaces stops And in the next proposition, this integer, which we have as m, actually is the dimension of our vector space V. So let me state that as a proposition. Here, let n be equal to the dimension of V and P be a linear operator. Then your T to the n, its null space, is equal to the null space of T to the n plus 1, and so on. Okay, that's what's trying to say. So this m here is in fact the dimension of the vector space V. The proof will be left. And then we have some remark. V is not equal always to the null space of T, direct sum with the range of our T for each T linear operator. But we have, of course, we know that this null space and this range space are the usual subspaces of V. But here, what subspaces of V can we express V as it's as their direct sum? This is answered by the next proposition, which states that if we have a linear operator and we have the dimension of V as n, then your V is expressed as the direct sum of the n power of T, the null space of that, with respect to the n, the range of the n power of T. Okay, the proof here is the first part is to show that the intersection is just of T to the n, and the range T to the n is just the zero vector. And then the second part is it follows from the definition of direct sum, and then show that V is a sum of the null T to the n plus range T to the n, which is clear from the context, because when you have this is from definition 1.45, and also then the third is that we have to show that the dimension of this, let's say this is A, is equal to the dimension of your V, and then that's all. The first, you have to show that their intersection is 0. Then the second one is you have to show they are this null Tn plus range Tn is indeed a direct sum. So let me rephrase that. is direct sum. And lastly, we have to show that the dimension, if we have this as A, they agree with each other. So the first one is the following. So for one, let V be an element of the null T to the N intersection range T to the N. This means that T to the N of V is 0 and T to the N of U is equal to V for some U in V. Okay. Now, if we apply T to the N to both sides in this equation, if we have T to the N of V is equal to T to the N. This one, T to the N of V, what do you get? You get 0 is equal to T times raised to 2N V. This implies that T to the N is also 0 by our previous proposition here. Thus, this means that V is equal to the T to the N of VU is equal to 0. Hence, your the intersection of the following is just 0 vector. And then the number 2 is clear. And number 3 is easy because we have the dim of the null T to the N range T to the N. So clear that null T to the N plus range T to the N is direct sum. Okay. We already have this one is a sum, and they are direct sum. Now we are left to show that indeed this direct sum is equal to the vector space. Okay. So this dimension is just equal to the dimension of the null of T to the N plus the dimension of range T to the N, which is equal to 1. This is just the fundamental by our fundamental theorem of linear maps. And thus your conclusion is the null of T to the N range T to the N is indeed equal to B because the invariant dimension. They determine like by the fundamental theorem of the linear maps. Okay, this is the proof of V being direct sum. Let's quickly brush up with a computational example so that we will be guided with our next concept, which is the concept of generalized eigenspace or eigenvector and something like that. Okay. For an example, let's have the book example. T Z1, Z2, Z3, 4, Z2, 0, and 5, Z3. So T here is a linear operator on F to the 3. Now, the null of T is just Z1, 0, 0, Z1 in F, and the range T is, again, this is Z2, 0, Z3, Z2 and Z3 in F. This null space of the intersection, the range D is not just the zero vector. So here, not direct sum. Why? Because you can check that the intersection is not only the zero vector. For example, Z1 is also in Z in the range, and then this one is in the range D and also in the null space. So can't be the zero vector alone, given Z1 and none. Z1 replace it with Z2, and then Z2, 0, 0, and Z2, 0, 0 here is also in the range. If you set Z2 be Z1 be equal to Z2 and Z3 be 0. Okay. So Z1, if Z1 equal to Z2 non-zero and Z3 equal to 0, Z1, 0, 0 is both in the range of T and also in the null of T. So this is just an example. However, if you have T to the 3 of Z1, Z2, Z3, you will just get 0, 0, 125. So 125 here is just 5 raised to 3, Z3. Of course, Z3 is a field element. Now, this null space of T raised to 3 is this one, Z1, Z2, and 0. Z1, Z2 are field elements. And then the range of T raised to 3 is just 0, 0. Like, let's name the variable Z3. Then Z3 a field element. And check that the null of T raised to 3 plus range of T raised to 3 is equal to our vector space Z1, Z2, Z3, which is, okay, this is just F to the 3. This is a clear from what we have already experienced so far. Now, let's dive to the next concept of generalized eigenvectors. So, some operators don't have eigenvectors. So because of that, we want to make good alternative. In this section, we will introduce concept of generalized eigenvectors, which will play a major role in our structure of an operator. To understand why we need more eigenvectors, let's examine and the question of describing an operator. And then how do we describe them? We just decompose the domain into invariant subspaces. So if we have a V, and then let's say we have an operator V, we want to express V as U sub 1 and then up to U sub M. So this is called a nice decomposition such that each U sub J is a T invariant subspace. Subspace of the vector space V. And the simplest possible non-zero invariant subspace are one-dimensional. And then we know that our one-dimensional subspace are that one with which we have discussed before. And this is just we discussed this on the concept of eigenvectors and eigenvalues. So a decomposition here for each where each U sub J is a one-dimensional subspace which invariant under T is possible if and only if your V has bases consisting of eigenvectors of T. And this is possible if and only if V is just the direct sum of this is we have seen this before. Where each of these are distinct eigenvalues of our T. And then the spectral theorem shows that if V is an inner product space, spectral theorem says that this nice decomposition holds when F is just our C, we have for every what is this? Normal operators. And then when F is equal to R, this decomposition is true for every self-adjoint operators. Okay. That's why this is important, the spectral theorem. But here, sadly, the decomposition may not hold for general operators and even on complex vector space, which is like an example was given by the operator in before. That's not enough. Does not have enough eigenvectors to hold. For example, we will show later. For example, you have there are only the number of eigenvector does not the number of vector does not equal to the dimension, so it's not going on well. So generalized eigenvectors and eigenspaces, which we'll introduce, will remedy this situation. So now we will introduce the concept of generalized eigenvector. T, linear operator, and lambda eigenvalue of T, the non-zero vector, is an generalized eigenvector of T corresponding to lambda. Okay, let me put this B non-zero here. To lambda, if your V is non-zero and T minus lambda I to the J is equal to, or V is equal to 0 for some positive integer J. Remark here, J can be any integer, but the generalized eigenvector will soon prove that generalized eigenvector, but soon we'll show that this J is equal to the dimension of, in fact, our vector space V. Now, we have the generalized eigenvector. If you collect them all, we have what we call the generalized eigenspace. Of course, we adjoin the zero vector. So let's define it. So if the generalized eigenspace of T corresponding to our lambda, denoted G lambda T, is defined to be the set of all general eigenvectors of T corresponding to lambda, and we will adjoin the zero vector. Zero vector. So this is just, so zero vector will act as our zero vector. And then this is clear. The clear remark is that if we get our this is just a subspace of your generalized eigenspace. The eigenspace is subspace, the generalized eigenspace. Next proposition is the following. In fact, we can express this generalized eigenspace as just the null space of T minus lambda I raised to the dimension of our vector space V. As we have our eigenspace is just this read out the dimension of. In fact, the J earlier is the dimension of the vector space V. So let's prove this quickly. Suppose V is an element of the null space of T minus lambda I raised to the dimension of V. This implies that is your V is also the here. Now, if V is in G lambda T. There exists a J positive integer such that your V is in the null of T minus lambda I raised to J. And of course, from previous theorem, it will stop when V is already, this is from 8.4. The null space will stop growing when it reach the dimension of our V. So we will just replace our, instead of P of 8.4 with our T minus lambda I. So we get, this is 8.4 and 8.2. We get the V is also in the null of T minus lambda I raised to the dimension of V. And then we already show that G here is, this is inside this. And earlier we have this is inside this, and then that's the end of it. The next proposition is that we will have our remark before that a major goal is to show that we want to show that our vector space is expressed as direct sum of these generalized eigenspaces. Okay, for operators on finite dimensional complex vector space. So okay, this is the theorem. To formalize this statement, that's how this, let T be a linear operator and lambda 1 to lambda m be distinct eigenvalues of T, and V1 to Vm be corresponding generalized eigenvectors. Then your V1 up to Vm are linearly independent. Here I will leave the proof. I think I'll leave the proof. Because it's just checking linear independence. And then now I will go to, before moving forward, of course, this is when I say left, you have to read. And then, of course, I will just take this time to, of course, the main purpose, one of the main purpose of recording this video is for me to brush up my linear algebra before, and also sharing it with you. And what should I say? I would like to recommend the video by Erin. I think it's Erin first. Let me check. Okay. I would like to recommend.
And so now we have the definition of
Video by Erin Purse. I think he is more versed than me in discussing this video, but you can take a look at his discussion. It's better. But here I also discussed something. Maybe it's different level, but we essentially use the same textbook. Okay. On YouTube, this is linear algebra. This is the third linear algebra in their school. Okay, that's the end for generalized eigenspace. Now we go to the next topic, the nilpotent operators. So what are nilpotent operators? So T in is nilpotent if there exists an M such that your T to the M is equal to the zero operator. An example is the following. If N is an operator and F4 defined by the following, Z3 if Z1, Z2, Z3, Z4, this is mapped by N to Z3, Z4, 0, 0. Now, observe that N of this, that we call this Z, is equal to N of Z3, Z4, 0, 0. This is just zero operator. Here, N is nilpotent. And this is one example. Also, if we have differentiation on your polynomial of degree at most M in R, D plus 1 derivative is 0. So example, you have D over not D but M plus 1 derivative. The M plus 1 of F D of how do you M plus 1 X is equal to 0 since F has degree at most M. So D here is nilpotent operator. We have already discussed the differentiation as an operator on this vector space of polynomials of degree at most M in previous discussion. So one theorem before going further. Okay. N be a linear operator, nilpotent. Then if you raise M to V, you get 0. That is the nilpotence degree is the dimension of the vector space. Proof. Nilpotent implies that G0N is just V. Thus, your null space of N dim V is equal to P. This means that the dimension of our um um that means that your 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 null of the N raised to dim V is the entire vector space. That means if you input any vector from B into N raised to dim V, you get 0. This is true for n vector in V, and therefore this D, N raised to the dimension of V, is indeed your N raised to dimension V is 0. This means zero operator. It's not 0, but rather the zero operator. This is what you want. Now, this one is the proof here is like recalling, extending a basis of null space, and then after you get a basis of null space, extend this to a basis of the power of n, uh, the null space of n, and then extend it to the power of the null space of n raised to 2, and then to null space n raised to 3, and then you continue the same fashion so that you will end up with the null space raised to the dimension of V, which is in exactly V, and then work with the matrix of n with respect to this basis, and then you have a first column, and then you add additional columns at the beginning, consists of zeros because the corresponding base vectors are in null n, and then it's just something like well, you have this pattern, and then you repeat over and over again, and then you get the idea of it. And then I will leave the proof for reading assignment also. And then here is the proposition. If n is nilpotent on V, then there exists a basis of V such that with respect to this basis, n has matrix of form. You have 0 here, 0 here, then you get 0 in the diagonal, and below the diagonal. So this is the matrix of a nilpotent operator. This with respect to that basis. Okay, I think I'll end here. Next meeting, we will discuss the composition of operator. So what is the composition of operator? Here we will discuss V being direct sum of our eigenspaces, which we have sort of studied here, but not very stated very formally. I have already stated that. Let's prove that next meeting. And then we have the concept of multiplicity of eigenvalue T is just the dimension corresponding to the generalized eigenspace. That is the dimension of null T minus lambda I raised to dimension of V. So we will discuss more of that later, and then I think I'll end here.